Okay, that's great. Now, today, see, last time what we learned was Aloha and slotted Aloha, and they were actually, we can say, they were contention-based protocol. What is the meaning of contention-based protocol? Contention is what competition, right? So, what was the case? Like all of the stations were struggling to get a slot, right? So they were competing with each other to have a successful transmission. So that is known as contention-based protocols. So which are the contention-based protocols? So one of them is Aloha, pure Aloha. Then is slotted Aloha. Next is CSMA, right? Which is CSMA, CSMCD, CSMACD, and next is CSMACA. These are another contention-based protocols, but these protocols will be covered by Shital Madam, right? So, what is this category? This category is basically where the stations are competing with each other for getting a slot. Right now, we are learning the next category of the algorithm, which is collision-free protocols. What is that? So here, collision will not take place because here competition will not be there. So does that mean that we are having one station per channel? No, we are having multiple stations per channel, but still competition will not be there because there will be a reservation, right? What is the meaning of reservation here? That each station will have their own reservation to use the channel. So this is what collision free. So now if the channel is reserved for a station, that means there will not be any collision now. Okay, so which are these protocols? Such three to four protocols we will learn. Three protocols basically we will learn. One is the bitmap protocol. Next is binary countdown protocol, and the third one will be token passing protocol. Three protocols will be that we will learn. More than that are available, right? Variations of them are available, but we are going to learn these three, and then we will go for one more category of these protocols soon, right? So that is what today's plan is, to learn about these protocols. Okay, so now first is bitmap protocol. So this is, we are learning about the bitmap protocol. Okay, now what it is? So it is very simple one. It is a reservation kind of protocol. So what will happen? Suppose there are 8 stations in the network. We are having 8 stations in. We are sharing. They are sharing the channel, right? So we will have 8 contention slots first, right? So suppose I'm considering this 8 for each contention slot. There will be 8 stations. So for each station there will be contention slot. That is a small duration which is allocated to each station. Okay. So suppose I have machine 1, 3, and 7 out of these 8 stations, which are numbered from 0 to 7. There are 8 stations, they are numbered from 0 to 7. Out of this, there are 3 stations, 1, 3, 7, having the data. They are having the data to transmit through a same channel. So what will happen now? Suppose now communication starts. Suppose now my communication begins. Suppose now channel, all the machines are restarted and everything is fine now. So now what will happen? First, there will be 8 slots. Suppose I am considering each slot, contention slot has 1 microsecond duration. Suppose it is of 1 microsecond duration, so there will be 0 to 1 microsecond. There will be a contention slot from 1 to 2 microsecond, 2 to 3 microsecond, in such a way that 8 contention slots will be, and there will be 8 contention slots. That each contention slot is for each station. What is the meaning of that station? What will be done there? The meaning is that suppose station 1 has data to send, it is going to mark its own contention slot. This contention slot was for station 0, this contention slot is for station 1, and this contention slot is for station 7, right? So station 1, 3, and 7 is going to mark 1. They are going to send 1 in their reserved contention slots, right? And then so now what is happening? Now what is happening to other stations? Now other stations are connected to the same line. All 8 stations are connected to the same wire. They are all listening the channel, and they listen. Okay, from 0 to 1 microsecond there was nothing. That means 0 to 1 microsecond there was no voltage in the line, and that was the slot for station 0. That means station 0 doesn't have anything to send. Then from 1 to 2 microsecond, which is a contention slot of station 1, the voltage was high, so all the station will listen that okay, 1 to 2 is high, that means it was continuous slot of station 1, and hence 1 has data to transmit. So they will remember, okay, station 1 has data to transmit. Same way 2, for the slot for the 2, which will be from 2 to 3 microsecond, will be empty, and then from 3 to 4 second again it will be 1, that was a continuous slot for the station 3, so again it will be 1. So all in that way they are going to listen all 8 continuous slots. So all the stations now on the channel, they are sharing the channel, are aware that station 1, station 3 and station 7 has data to transmit. Okay, so now what will happen now, everyone knows that who has data to transmit. Okay, now lower number station will transmit first. That is again a protocol, right? That is again an algorithm. So that is what we will say, that lower number station will send first. So 1 will send first, then 3 will send first, and 7 will send first. As 7 also knows that there are 3 stations, totally we are 3 stations who wants to transmit. So it is going to wait for the duration of that is given to station 1, then that is given to station 3, and then it will start sending. So it is actually decentralized. There is no one who will control this, but everyone knows everything. That's why they are going to give the time to suppose 7 will give time to both of them, 3 will give time to 1, and then it will start. So this is how communication will take place, right? So now, so what will be the case? Like here, the time given to 1 will be fixed. Suppose it is sending d bits per second, so duration will be suppose it takes d, it wants to send d bits per are allowed to send according to data rate. Suppose this frame size is a d bit, and whatever the so that frame length will be fixed here. D bit frame length will be fixed here. Why? Because according to the data rate, they will come to know, okay, this much will be the time to send d bits. So they are going to calculate the time, that how much time will be taken, because data rate of the channel is also fixed. Okay, so bit duration, the length, frame length will be also fixed, and hence the time duration for a frame will also be fixed for all. That will be d bit. Suppose it is d bit, the data bits we are sending. Okay, then suppose this gets over, then again continuous slots will start, and again if 1 and 5 has data to transmit, so they are going to send again. Now after sending this, again continuous slots will begin, and again that suppose 2 has data to transmit, then it is going to send. So as I told you, that the length frame we have decided that is d, and suppose this is just 1 bit, so the duration of here also only 1 bit is required, right, to send 1 or 0. So whatever the duration, I told you 1 microsecond, but again it will vary. That will be the time to send one bit. That will be the duration for the one slot. Okay, so are you clear with the basic bitmap protocol? So this is actually bitmap. This is known as bitmap. The contention slot, this is bitmap. So what we are actually having, we are having frames, then bitmap, then again frames, then bitmap. What is bitmap? That in that bitmap, if I have data to transmit, then I will mark 1 when for the slot assigned to me. Are you clear with the scheme? Then I can go for the analysis, further analysis. Are you clear with this? Then I can ask you some questions regarding to this, so that we can analyze. What about others? All of you are clear? Great. Now, what is the case? So now question is, what is the efficiency of this scheme, right? So for that we need to so first question is, what is efficiency? That is my ultimate question. This is what I want to understand. But before that, let us understand that how much a station has to wait before it starts to transmit. Okay. So here the things will be different for lower number station and the higher number station. Why? Because see, this is fixed, lower number station, then this will be higher number station. Here lower number station will come first. So this scheme is quite dependent on number of station. Like the station number 0 will have different scenario to see, and station number 7 has different scenario to see. Okay, so let us learn that. Suppose I started my communication. I suppose my station is turned on. All the stations are turned on at this moment at 0 second. right? So this we can say, suppose it is 1 microsecond, second microsecond, so on. But as soon as I start, I don't have data to transmit. So assuming that at mid of this, suppose after 3-4 microsecond, I have data to transmit. This is my assumption. Okay, just for analysis purpose, I am taking this assumption. Okay, so can you tell me how much, how many slots, how many contention slots station, lower number station has to wait? Lower number station, that means assuming station 0. Okay, so how many contention slots station 0 has to wait before it starts transmitting? So can you tell me, suppose n stations are there, assume there are n stations, so n contention slots are going to come. Okay, now lower number stations are okay, so there are n stations, that means n contention slots will be there. As soon as my communication starts, I don't have data to transmit. So initially, will station 0, my data becomes ready with me at this location, at this moment. Okay, so what station 0 will do in this slot? As soon as it will start, it will have its chance to transmit. So what will be 0 send? Will it send 1 or it will not send anything? Station 0, will it send anything or it will not send anything here? It will not send anything, right? So, and we are assuming here it is a low load. Low load means what? This is another assumption that we are having, low load. What is the meaning of low load? What is the meaning of low load? And high load, what is this terminology says? What do you understand by this? When we say low load, that means how many number of stations ready to transmit will be less or more? Number of stations that has data to transmit will be less or more? Low load, I am considering lesser amount, lesser uh, uh, low load. That means we on the channel there are less number of stations that are ready, right? Keval, are you clear with low load? So yes, number of stations will be less. So assuming that it is a low load, so assuming only station 0 has data to transmit, but that also it starts, it becomes ready at this location, and no other station is ready. Why? Because we have considered the low load situation. We will go for the high load later. Okay, so what will happen here? It will be empty. No one will send anything because no one has data to send. At this moment, station 0 will become ready. But now what will happen? No one has no one has marked anything because 0 cannot mark here. Though it is ready, but it cannot mark here. So now what will happen here? What do you think? What will happen here? That means everyone knows that no one has data to transmit because no one sent anything in the contention slot. So what will come here? Will it be frames or will it be next contention slots? What will followed by contention slot for first this next slots? Yes, next. Yes, it will be next slots. So because no frames are there, then again contention slots are going to come, right? No one wants to send anything, so they are not going to wait for anyone. Next contention slots will begin. Okay, so so again now what will happen? So now who will send? Suppose again there is a low load, only station 0 is ready. Now what will happen? So frames are not there. Again, these contention slots are going to come here. There are n contention slots, right? There are n contention slots. Now tell me what 0 will do? What 0 will send? Here it will send 1. No other station will send anything. Nothing will be transmitted here. Why? Because no one else is ready. And then station 0 will transmit. Then station 0 will transmit. So can you tell me before sending data, how many contention slots station 0 waited? How many contention slots? Is it 1? How many contention? And see, there are n station. This is 1 contention slot. This is second contention slot. So already we are having n contention slots. Will it be 7? What is my question? Before sending data, how many contention slots station 0 waited? 16. 8 is not the correct answer. 7 is not the 16. You are near. Think over that. When? So why you are considering 16? Because this n plus this n, right, Vimal? This 8 and this 8. Are you considering those in that way? You are considering 16? Huh. But station 0 was not waiting here because data was not ready, na? So it was almost at n by 2 the data was ready. So how many total stores it was waiting? Waiting will be when you have data and you will transmit, right? So how many total slots you will wait? Yes, it will be actually go in terms of n. How many? Because it is not related with this, or in general we can say almost it will be 1.5 n, 3 by 2 n, n plus n by 2. Yes or no? So it will be 3 by 2 n roughly. Roughly it will be 3 by 2 n. All of you are clear with this? 1.5 n slots, lower number station on an average, roughly it will wait 1.5 n slots. This n slots and 0.5 n slots here. Clear? We don't have data in previous contention slots, then it does not consume any time. Then how can we say 0? No. See, as a station 0, I was ready at the 4th microsecond. Yes or no? Suppose at the 4th microsecond I was ready. At 0th microsecond I was not ready. When I will get chance to transmit, that up to 7 microsecond it will get completed. Then again more 8 microseconds will pass, and then I will get chance to transmit. So this n slots, that n microseconds and n by 2 microseconds I am waiting here on an average, roughly. So 3 by 2 n slots I waited, then I could transmit data. Actually, I'm not interested in transmitting contention slot is extra. It is just for avoiding the what we can say. It is just for avoiding the overhead. Yes or no? I mean, it is just for avoiding collision. It is just overhead. It is just for avoiding the collisions. Is it making sense, Priyank? Waiting is what? Like I am ready at 4th second, then I will transmit at this moment. So I'm going to wait this many slots, na? Is it clear, Priyank? If not, then you can unmute yourself and you can ask, because time typing can consume the time. If we have 1 and 0 in contention slots, take the same time. If we have 1 and 0 in the contention slots, I'm not getting.
Hello, ma'am.
Priyank.
Ma'am, if we have 1 in the condenser slot of like data 4, then it will take time to transmit.
Wait. Where you are asking to have 1?
Means any condenser slot, if we have like data to transmit, for example, in the first condenser slot we have data in the first and 3 and 7, then it will take time to transmit the data. So if we don't have any data to transmit, then it will take less time. Then how?
Listen. What I'm asking in this example, I can explain you that what is happening. See, in this example, then you can ask me once again if it is not clear. See, here my data was ready. Here my data was ready. That's why as a station 1, my data was ready. Here in this example, station 1 has data to transmit. That's why it sent 1. Okay. Now, so now data is ready. So here it is sending 1. I have data to transmit, but it is not sending the data, right? It is just telling others that I have data to transmit. So here data was ready. Then it waited for 1 microsecond, 2, 3, 4, 5, 6, and 7 microsecond, and then it got chance to transmit. Is it clear to you? Right? Suppose now I am considering for this. Here it was having data to transmit, assuming that here it was ready. Suppose, so how many slots it waited? It waited like here it transmitted this many slots, and this slots whatever time this consumed, and then it got chance to transmit. Yes or no? Suppose station 3 was ready here. And but here it is not, it's contention slot even. So it will wait for these 2 contention slots. Then it will send, yes, I have data to transmit. Then again it will wait for others. Then it will wait for 1 to transmit, and then it will send. So it will be understood. So in that way, if you are considering that my station 0 was not ready here, my station was not ready here, it became ready here. and no one else was ready. These many assumptions are there. So what will happen? It will wait for n by 2 slots. Then this will not be there. These slots will come here. It will send one. No one else will send, and then it will send data. So n slots, n by 2 slots. So totally 3 by 2 into n slots. Is it clear? Okay, great, great. Now let us go for okay. So everyone is clear with 3 by 2 n slots. Great. Now tell me for the lower numbers, higher number station. Tell me, this is rough estimate. This is not the perfect perfect estimate, right? Roughly for higher number stations, take higher number station 7. Again, the same assumption. All the station starts at this location. Station has data at this moment. Immediately, as soon as you turn on, they don't have data to transmit. But it takes 3-4 microsecond to gather the data to transmit. But it is higher number station. So how many slots will it wait after generating data to send its frame? Assuming only 7 has data to transmit. Data becomes ready here. So start your waiting time starts from here. So now it will wait for this microsecond, this microsecond, this microsecond, and it will wait for this microsecond. Even it will say, yes, I have data to transmit. Now can it send? No one else has data to transmit. Only 7 has data to transmit. Now can it send? Yes. So how many slots it waited after becoming ready? 4. If it is n by 2, we can say it is n by 2. Yes, it will be n by 2. So it was lower number stations are waiting for 1.3 n slots. Higher number stations are waiting n by 2 slots, right? Roughly. So on an average wait time will be how much? So half of the stations are lower number, half of the stations are a higher number. So what we can say, on an average, half stations are waiting for 1.5 slots, 1.5 into n slots, and half of the stations are waiting for n by 2 slots, that is 0.5 slots. So on an average, each station is waiting for n slots. Average, rough estimate of this average, right? Half stations are waiting for 1.5 slots, and half are waiting for half slots into n, of course, in both cases. So in general, they are waiting for n slots before transmission in the low load situation, right? Okay. So after waiting, how much? So now what is efficiency? I told you to we want to find out efficiency. What is efficiency? It is useful divided by total. Useful data bits divided by total data bits. Can you tell me what exactly, how many bits are useful in the low load? Useful divided by total is the efficiency. What suppose it is lower number, so suppose it is low load, right? So what will happen here? Station 0 will send D bits, right? After waiting this slots, n by 2 slots, and n slots. So can you tell me how many bits were actually bits were useful here? How many bit slots or timing that we have spent in the channel? The channel was utilized for the useful amount of data for how many bit durations? How many bit duration were useful here? See, this was contention and for this is not useful data. This is overhead, as I told you earlier, right? This is required just to avoid collisions. This is required because the channel was shared among many. So to avoid collisions, this was required, right? But useful data, the actual utilization of the channel is for D bits only. That is the original data that was for what channel was meant for. The channel was designed for that, sending this amount of data. Actual frame is of D bits duration, right? For channel was utilized for the useful amount of data for the D duration, right? And what is the total duration of this? So we can say that on an average station waits for n contention slots and then it sends D bits. So it will be what? N plus D. So that will be n durations n plus D. So now I can explain this. I can explain this in better way. See, on an average, each station waits for n contention slots and then it sends the amount of data. Then again, a next station has low load. That means only one station at a time is ready. It can be higher number or it can be lower number. If it is higher number, then it will be on an average waiting for 0.5 slots, 0.5 into n slots. and if it is lower number, it is waiting for 1.5 into n slot. But on an average, each station is waiting for n slots before transmission. Transmission is the actual purpose. How many bits we are transmitting? It is fixed d duration, right? So how you can see your channel as n slots are used for contention, resolution of contention, then d duration is useful. Again, n slots are used for the contention, and d duration is for the actual data. So actually your efficiency will be d divided by n plus t. Are you clear with this efficiency equation? Is it making sense to you, this efficiency equation? Then I can give you the next version of it. That's why I'm asking. Anything should be explained here? Okay, so now question is to you is, what about high load? Suppose it is not low load, if it is high load. What is the meaning of high load here? High load is, let me explain that here. High load, that means every station has data to transmit. That is what high load is, that everyone has data to transmit. So what will happen? Suppose every station has data to transmit, right? So let us assume that every station has data to transmit. It is high load. Lot of data is there, right? Lot of data is there. All the station has data to transmit. So all of them are going to mark 1 in that contention slot. And how many frames will be followed by them? Followed by these contention slots? How many frames will be followed by contention slots? N frames. So what will be the, yes, N frames are going to come. So can you tell me what is useful duration divided by total duration? What is useful duration here? Useful duration is where data is actually getting transmitted. What is that? Each frame is of d bit duration. Such, and yes, it will be nd. Nd will it be n plus d? Abhi, it will be nd. This is d. Then next is again d. Again d. Such n frames are there. So nd will be the n into d will be the useful duration. Are you clear with that, Abhi? Right. So useful is nd. What is total? What is total? I want to know efficiency. Nd plus n. Yes, it will be nd plus n because this will be n. So nd plus n. Can you simplify it further? Can you simplify it further? It will be d divided by, if I take n common, it will be d divided by d plus 1. Right? So that you can understand that each station is actually sending d frames, and it is waiting for one contention slot for itself. Right? Extra one slot. I mean, in that sense, you can one slot of d. So it is okay. Like I am waiting. If it is a high load, that each station sends d data and it waits one more. I mean, it is extra 1 bit duration. One bit duration is also only it is waiting, right? So for high load duration, this is okay. If, that is fine. But for low load duration, this is the efficiency. Can you tell me, bitmap protocol is more efficient in high load or low load? D divided by n plus d and d divided by it. Yes, it is more efficient in high load, and that is what should happen. Now see, if it is high load, then reservation helps. Like everyone has data to transfer, so chances of collision will be high. Right? Everyone will send, so sorted aloha or any other protocol that you will learn in future will not be useful, right? But if it is a low load, then aloha is also okay. Like only one station at a time is ready. So as soon as you are ready, just transmit it. So that is going to help, right? So what we are concluding here, that if it is a low load, then contention based protocol where competition happens, but low load, that means there are less number of stations who they are competing for each with each other, they will be more useful. But if it is a high load, then reservation based protocols are more useful, because here you are not giving chance anyone to reserve the channel. And why that is not useful? Because you already the stations are not having data to transmit. So don't waste time to ask them that do you have data. So in that sense, this is more efficient. So this is very much useful statement, will be useful in future. that collision free protocols, where one of them is bitmap, is more efficient in high load, and contention based protocol aloha, slotted aloha, csma, csmcd, csmca are more useful in a low load situation. Okay, so this is all about bitmap protocol. Now we are going for one more protocol, which is a binary countdown protocol. A very simple protocol here. What it is, suppose I have um, 16 stations, right? So their address will be 16 stations. So this is my n, right? So their address will be from, say, station. So I'm giving number of station number 0 to station number 15, right? So this is how I have 16 stations. Now out of that, station number 2, station number 4, station number 9, and station number 10 are ready at a time, as here multiple stations were ready, 1, 3, 7, like that, right? Now what is binary countdown? First they will compete, they will decide that who will send first. Okay, so these stations are ready, so all of them are going to send first bit of their address, right? So they will send, so this will send 0, this will send 0, this will send 1, this will send 1. First bit of their address they are going to send. In the first bit duration, they will send first bit of their address. And ORing will take place in the channel. From all of this data, OR gate will be placed. So ORing will take place. So what will be OR of this data? 0, 0, 1, 1. What will be OR of this? 0, 0, 1, 1. What is OR of this? 1. So answer will be 1. So this two station will come to know, okay, there is some number, there is a number which is having higher value than higher address than me. Why they will know? Because my first bit is 0. My first bit is 0, but ORing result is 1. That means there must be a station who is competing for the channel having 1 on the first place on the MSB bit. If it is having 1, that means they are higher number station, and higher number station sends first. That is what the rule is, right? In binary countdown, as the name suggests, it is counting down. First higher number will send, then the lower number will send, and then in that way the communication will happen, right? And so these two will come to know there is a station which is having higher number than me in the station number. That's why we should not send. So they will stop competing. They will stop sending. But here the result was 1. So 9 thinks that, okay, that 1 was because of me. 10 thinks that 1 was because of me. So what will happen next? They will send the next bit. They will send next address. Yes, they will send the next second bit. They will send. So answer is 0, right? Because 0 or 0 is 0. So again, still they are confused that whether this 0 was for me or because of this type of situation. So they will continue to compete, and the result will be what? They will compete for the third bit. They will send the third bit, and here they will come to know. That okay, answer is 1. So now this will come to know, this station 9 will come to know, no, this was not because of me, because there is one station having higher bit than higher value at this bit than me. So it will stop competing, and station 10 continues. It continues to it continues to send, because still it is not sure. I mean, it has to check whether the last bit is also there is not any other conflict. So it will continue to send, but this 3 will not send. So answer will be this only. That will be 1010. That means on the channel, address of station 10 will reflect, and hence 10 will send. Okay. So this is how, this is what binary countdown protocol works. So what is the logic here? That higher number station sends. How to send? That send first bit, right? And or them, right? If the result is higher than your, I can repeat from the second bit. See, second bit. Okay, now what will happen? Both of here, these are not going to send. Are you clear with this? This will not compete. They will stop competing. Are you clear with that? So you are not clear with, see what will happen. See, the scheme is what? The scheme is that, like, I will send my first bit. MSB bit. All of the stations will send MSB bit, right? And then ORing will take place in the channel. Okay, and OR result is higher than me. That means there is a station who has higher bit value than me, right? Here, or what will happen here? OR result is 1. Why the OR result was 1? Because some station was there who had one value here which was higher than me. When the one value will be here, definitely the number will be higher. When MSB has value 1, it is of course higher than the MSB value 0. That number will be higher than MSB value 0, right? So they will come to know, okay, that there is a station who has higher number than me. That's why I should stop sending, right? So these two stations are going to decide that now we will not send. Are you clear with that, Priyank? Okay, so now these two will decide. How protocol no see yes, no, it is not necessary that no one knows that who is ready. It is possible that station 1, 3, 7 and say 1, 3, 7 and 8 are ready. Suppose these stations are ready. Protocol doesn't know anything. What is protocol? Suppose 1, 3, 7, 8 are ready. That is individually 1, 3, 7 and 8 are ready. Suppose I am ready. I am station 1, right? So what I will do, I will send my whenever the contention slot will begin, whenever the 0 time, suppose the 0 time contention slots begins, right? So at 0 time, what I will send my first bit. What will be my first bit to transmit here? Dev, what will be my first bit to transmit here? 0. What will be, as a station 3, what will be my first bit to transmit here? 0. What will be my first bit to transmit here? 0. And what will be my first bit to transmit here? 1. Okay, so now who will stop sending now? Which station? Now ORing will take place, right? What will be the result of ORing? What will be the results of ORing here? 1. So now that OR result of OR will be also kept on the channel itself. So every station can listen that, right? So every station heard that, okay, result of OR is 1. That means what will be the decision of 1? Yes, 1, 3 and 7 will stop. Are you clear with this there? 1, 3 and 7 will stop. 8 will continue to send. But 8 will also, of course, 8 is going to complete it because it is not knowing that it is possible that some station is having number 9, right? So it will continue to send. 8 will not stop. It will send till its complete address is reflecting on the channel after ORing. 8 will not stop. It will send the next bit. It will send the next bit. It will send the next bit, and it will realize that, okay, after ORing, only its address is reflecting, as the address of 10 was reflecting on the channel. Here also, address of 8 will reflect on the channel, and it will come to know that I'm going to send. Is it clear? Should I elaborate this with another example there, or are you clear with it? Great. Okay, so now what is the efficiency here? What is efficiency? So after this, what will happen? Suppose 100 is getting transmitted here. Then what will happen? These 4 bits are transmitted. Then what will happen here? On the channel, these 4 slots are utilized. Right? What will happen next now? On the channel, what do you think? What will happen? Suppose these stations were ready. Now 8 is going to send. Now what will happen on the channel? Transmission. Yes, transmission. How many bits? Assume that only D bits are, the frame length is D bit. So D bit will get transmitted. Right? Then what will happen next? D bits get transmitted. Who will transmit these D bits? Be quick. Who will transmit these D bits? All of you. The question is to all. Yes, 8 is going to transmit D bits. Now what will happen on the channel? Use your logic. See, don't go by the words and what do you think that? Yes, check again for 137. Not second bit of 137. No, not a B. Check for the next station. Again, compute. True. See, check again for 137, but not necessarily 137. Now there will be next competition will take place, but 137 will be there. But possibly if 9 is ready, it is also going to come in the competition. Suppose in this duration, during this time, 9 becomes ready. So it is also going to come. It is not like for 137. But yes, it will be competition for next ready stations. right? Next ready stations, the computation will take place, right? And it will begin from the first bit only. It will not be like wherever you stop from that you will start. No, because you don't know which other stations are ready, right? So you will start from the beginning again, from the first bit. Every station will send their first bit, second bit, so on. Is it clear, everyone? Now tell me the efficiency. First, tell me how many slots will be there. Suppose n stations are there, how many slots will be utilized here? If there are n stations, how many slots will be utilized here? Okay, so how, if there were 16 stations, how many slots utilized here? 4. How that 16 to 4 came? So it is log n to the base 2. Is it clear? Log n to the base 2. So what will be the efficiency here? D divided by log n. Why? Because it is address. How many address bit will be required? Log n to the base 2 plus d. This is the efficiency. Are you clear with this? Okay. Now sometimes what happens that this is frame to transmit, right? And can I say this is source address? 8 is the source and this is 8 bits to transmit, right? This was the source and next followed by its own data frame, right? So in generally what happens when we send a frame, in that we send source address as well, right? So if we are adjusting our frame structure such a way that first in the frame itself, first source address is going to come, then source address is going to come, then what will happen, then destination address will come. In that way, if we are adjusting the frame or frame structure we design like that, then what will happen, we can utilize this n bits as our frame data only. Then we should start sending our frame from the destination address itself, right? So even we are not wasting this even, so you can have 100% efficiency. This is possible. 100% efficiency is possible here, right? How? By considering this bit slots as part of your frame itself. Why? Because it is source address only, right? And source address, we should just design, your receiver must understand that first 4 bits will come. If there are 16 stations, then first 4 bits are going to come as your source address. So this is your source. So do not ignore these bits. You listen these bits as well. This is your source bits, source address bit. So this will be again part of your useful data now, and then your efficiency will be 100%. Now we are going for the next improvement of this algorithm, which is mock and word variation of a binary countdown. Ha. No, there is not a solution. That is what we are doing here. That is true. Starvation is an issue because lower number station will never get chance possible, or very occasionally will get chance, and that is the solution here. That is what we are discussing here. So let us assign the virtual station number. Starvation is the issue. So let us assign the virtual station number. Like these are the stations, and assign this station numbers. Like assign 7 number to this, 6 number to this, and 0 number to this. So this is virtual station number. This is not actual address. This is virtual address, right? Now suppose, so what is the address here? So station D has address 5, right? Now suppose D sends. D in whatever competition happens, in that D is a higher number station and D sends. So now change the address of D to virtual station of address of D to 0. So now send D here. Send D at the last and make its address 0. What should be done with this virtual address now? What should be the virtual address of F now? 1. Yes. So what this will be 1. This will be 2. Improve the virtual addresses of this, right? And make this 0. What will be a virtual address of C and H? What should be virtual address of C? As it is? Yes, it is going to be as it is, same, right? So what is the logic? Those who sends change its virtual address. Now you will get the chance at last, so that everyone will get the chance. Is it clear? Is it clear to you, everyone? Now, see, that's good. Now, what should be now next is the limited contention protocol. See, I told you na, that this collision one more protocol is remaining, which is token passing, which is also collision free protocol. Token passing algorithm is there. I will explain, but later. But before that, third category of which is also collision free, it is also reservation based protocol. But before we move to that, we should learn one more protocol, one more category, that is limited contention protocol. See, one category is contention based protocol, next is collision free protocol, and third is limited contention. It is contention but in limited manner, right? Why we need this category? Because we are greedy. We know that Aloha, which is contention based protocol, which are good for low load. Collision free protocols are good, reservation based protocols are good for the high load, right? But let us combine both of them. Let us make a protocol which is acting like contention based protocol on the low load, and it is acting like collision free protocol for when it is a high load, right? Because it is possible that my network might have low load at some time and might have high load at other time. So if I'm taking any one category from the previous one, I'm going to suffer in the other one, right? So in the other situation, like it is contention based, in low load it is going to work fine, but in high load I'm going to suffer. Same is true for the collision free protocol. For the high load it will be good, and for the low load I'm going to suffer, right? So let us have a category which is limited contention protocol, which will act as a low load in the what we can say in the duration of low load, and it will act as a collision free protocol in the high load. So now what we are going to do, so for that what we will do here is assigning so what we will, so now we will group the stations. Assume that we are grouping the stations, right? Not necessarily disjoint group. One station can be member of multiple groups, right? So what will happen, like suppose in slot 0, for slot 0 I am having that member of group 0 will compete, right? And if anyone can send from that, that is good, right? And so communication will take place. Now in slot 1, again member of group 1 will send, okay? In group, in slot 2, member of group 3, member of group 2 or group 3, whatever you can give the number, the in that slot only those number who are member of that group will send, okay? Now suppose slots goes free, or if slots goes free, or collision happens, then it will be unsuccessful one. It will be so if it is a free slot, what is the meaning of that? If the slot 0 goes empty, what is the meaning of that? There is no member in group 0 who wants to send anything. And suppose collision happens, what is the meaning of that? There are multiple stations in group 0 who wants to transmit. Are you getting? So here what we are having limited contention. We are out of n station, I am making 5 groups. So in each group, suppose I am having n by 5 members on an average. Again, it is not necessarily disjoint group, so it can be more than that, but on an average I am having n by 5 members. Only n by 5 members are competing here, okay? Then for the next slot, again n by 5 member will compete on an average. Again, it can be more than that, right? So now so this is a basic idea, right? But now we can, so you will say how, okay, fine, that is okay. Limited contention is clear, that limited, you are assigning, you are reserving a slot for each group, 1, 2, 3, 4 and 5. So there is a slot reserved, but still there is a competition among the members of that group, right? So this is combination of both. But how it is going to help us in the case of low load and high load, right? Suppose it is low load. So now what I am going to do here, I am going to, low load means what? Very less stations will be ready. So I am going to keep my all n stations into one group itself, right? So now can I say it is like contention based protocol only? Now all n stations are in one group. What is the meaning of that? Whatever slot I am having, for that slot, all n stations are competing. But it is a low load, so there will not be any issue. So can I say it is like Aloha only? As soon as you are ready, just transmit it. Or it is slotted Aloha, in your slot, just transmit it, right? So if it is if it is a low load, then how I will group my stations? All the stations will be grouped in one. All the stations will be placed in one group. And suppose it is high load. So how I am going to group? I am going to create not 5 groups. I am going to create n groups. What is the meaning of that? N stations, n group. What is the meaning of that? Each station, in each group, how many members are there? Only one member on an average. So I'm how many slots I'm going to reserve? N slots. I'm going to have n slots, and for this slots, for this slot, a member of group 0 will compete. But in how many members are there in group 0? Only one member. So no one is going to compete with this, and hence 0 will transmit. Is it clear to you? So actually, you can say this slot was reserved for station 0. This slot was reserved for station 1. Right? If it is a low load, how to group? All the stations should be kept in one group. So all of them are permitted to send here. If it is high load, how to send how to arrange this? If it is high load, then each group will have only one member. So now what is the concept? The member of that group will compete for the slot. So only one member in a group, so no one will compete for the slot. That slot is actually reserved for that station. Is it clear to you, everyone? Limited contention is clear to you? So now, if it is a low load, I need to group accordingly. If it is high load, so my router has to just observe, or just we need to observe the network, and runtime we need to decide that how the grouping should be done. Are you clear? Yes or no? Then I can go with the proper example. One more example. Are you clear with the concept? Then I can give you example. We need to go with the example. Are you clear? And should I repeat? Let me know your status, otherwise this example is going to be your self-study, because I think you are not answering this. Are you going to tell me about, what is your status? Using example, it will be more clear. See, example is not based on, this is modified one. This is modified one. See, this concept is modified one. So, see, what is the concept here? Very basic concept. See, what is the limited contention protocol? That you will divide the time in slot. Each slot is reserved for a particular group. Suppose I have n groups. Suppose I have k groups, right? So I will have k slot. So slot 0 is reserved for member of group 0. Slot 1, in that way, k slots are there, and all k slots are reserved for particular group. What is the meaning of reserve for the particular group? Like in 0 slot, only member of group 0 will compete with each other to transmit. Okay, right? So suppose in group 0, station 1, 2 and 3 are there in group 0. So 1, 2, 3 station will compete for slot 0. Right? Station 4, 5, 6 are in group 1. Then when the slot 1 will come, the competition, if 4, 5 and 6, if they are, if any one of them is ready, they are going to compete for this. They will try to capture this, right? Suppose 4 and 5 are ready together. That means there will be, suppose now station 3 is ready. 3 is ready to send. Station 4 is ready to send, and station 5 is ready to send. So what will happen here? In slot 0, 1, 2, 3 will compete, right? So 3 can send. Why? Because 1, 2, 3 will compete, but 1 and 2 doesn't have data to transmit. So 3 will send data without any problem. Now in the next slot, what will happen? Suppose 7, 8, 9 is in group 3. Suppose 7, 8, 9 is in group 3, right? 7 has data to transmit, right? 7 in group 2. In group 2, 7, 8, 9 is there. So this slot is for 7, 8, 9. So now in this slot, who will compete? Only 4, 5 and 6 are permitted to send in this slot. 7 is not permitted to send in this slot. right? So what will happen? Who will compete? What will happen in this slot? 4 and 5 both will transmit. So collision will take place here, right? Now in slot 2, what will happen? Who can send? Only 7 can send. Why? Because this is reserved for 7, 8, and 9. And 8, 9 is not having data. Only 7 has data. So 7 can transmit here, right? In that way, all k slot will get completed. When again it will again there will be slot for 0, there will be slot for 1, right? So here again what will happen? From 4 or 5 anyone will transmit, because again if there is a collision they will wait for random amount of time, and whoever whose time will get completed first early, that session is going to send here. And again if both of them are ready together, again collision is going to take place. Is it clear to you? So now suppose 10 stations are there. If 10 stations are there, then I am assigning all of them in one group only. So only one group is there, group 0. So there will be slot for group 0, then there will be slot for group 0 again group 0, because there is only one slot, right? Now all the stations are in that group only, 1 2 n stations. So who will compete for this slot? Who can send in this slot? All the stations can send. So can I say in this slot you can all the stations can send, in this slot on the station can send? Can I say it is slotted aloha? Can I say it is slotted aloha? At this slot everyone is permitted to transmit. Are you clear with this? Okay. Now suppose I am grouping like that. In group 0 only station 0 is there. In group 1 the only station 1 is there. In group 2 only station 2 is there. In group n there are station n is there. Only one member in each slot. Now how many slots will be there? Slot 0, there will be slot 1, there will be slot 2. In that way how many slots will be there? N groups are there, so n slots will be there. In group 0 who can compete, who can send? In group 0 who can send? Who will compete? Only 0. Why? Because only one member is there. So can I say here 0 will send, here 1 will send, here 2 will send? Can I say it is reservation based protocol now? Understood. So now this is actually so this is what limited contention is. In when if there is a low load, keep all the stations into one group so that it will be contention based protocol. And when the high load is there, make a group such a way that only one member is there in the group. Understood, everyone? Should I go to the next example, modified version of the same? Okay, now there is adaptive tree work protocol, which is also limited contention protocol. Okay, it is using depth first search. DFS tree, depth first search you are going to apply, and assume that station A, station C, and station F, and station GH, station G. Suppose these stations are ready at this moment. Suppose here suppose I am ready. Which stations are ready? So station A, C, F, G are ready. Now what to do? You distribute. Suppose you are having this many stations A, B, and all the station. Now you see them as leaf node of, or you can say you just see them as endpoints of your binary tree. You just create this type of tree, so that what will happen? These two are under one common node, then these two are under one common node. In this way, you just assume your network is like this. Okay, create this type of tree. Okay, now what you will do? You will assign slots. So now this type of tree is created from the available stations, and you know that station A, you have in your mind that A, C, F, and G suppose are ready at this moment. Okay, so in slot 0, in the first slot, who can transmit? So in first slot, all the station under this node can transmit. So which are the stations under this node? Who is under this node? Which stations which are ready to transmit and who are ready to transmit? A, C, F, and G are ready to transmit, and all the stations who are ready under this node can transmit in slot 0. So who can transmit? 2, 3. But actually, ultimately, these stations are under this node itself, right? All the stations are so who can transmit? A, C, F and G can transmit. A, C, F, G can transmit here. Right. All of them can transmit. True. True. Now, so here, if all of them will transmit, what will happen in slot 0? Will it be collision free or there will be a collision? In slot 0, what will happen? If all of them will transmit, what will happen in slot 0? Will there be collision in slot 0? Okay, there will be collision, right? So if collision happens, go depth first. Go depth first. So you will go with slot. So in slot 1, in the next slot, who will get the chance? Who will be verified? Who will be examined? Node 2 will be examined. When node 2 is examined, that means all the stations under node 2 which are ready can transmit. So who will transmit in slot 1? Who will transmit in slot 1? Yes, they will transmit A and C. Will there be a collision or it will be collision free? Will it be collision or it will be collision free? There will be collision. If collision happens, then go depth first. If collision happens, then go depth first. So who will get chance now? In next slot 2, who will get chance? Which node will be examined? Which node will be examined? Yes, node A, node 4 will get examined and hence A will get the chance. Will there be a collision? Will there be collision? No, A can transmit without any issue. So now in slot 3, other child of the examined node or sibling of the node that you examined is going to verified. We are going to examine the sibling of the examined node. So who will get the chance? Which node will get examined? C will get the chance and which node will get examined? 5. So all the nodes under 5 will get the chance in node slot 3. But so C and D will get chance, but only C is ready, so C is going to get. So will there be any collision? No. So now what will happen? Now sibling of the last examined node will be verified, but now we don't have. So we will go to the parent node and we will check its sibling, right? So 3 will get the chance in the next slot 4. Slot 4. Who will send here? In slot 4, who will send? This will get examined? Yes, not 6 and 7. 6 and 7, but which station will send? Yes, F and G will send. F and G will send. So there will be collision. So if collision happens, then what to do? Who will, in slot 5, which node will be examined? If collision happens, depth first, right? So who will get examined? 6 will get examined, yes, and F will get the chance, right? Okay. What about assume that H is also ready? Assume that H is also ready. In sixth slot, what will happen? In sixth slot, what will happen? This has transmitted. This has transmitted. Now in sixth slot, what will happen? Who will get the chance? Who will be examined and what will happen? Who will get the chance? Yes, G and H will transmit. True. And then what will happen in the seventh slot? G. And what will happen in eighth slot? H. So everyone is ready getting. So how many contention slots required to solve the contention? How many slots required to solve the contention? 0 to 8. How many slots required? 9 slots were required. Yes, 9 slots are required. 0 to 8 slots, na? 0 slot, 1 slot, such 8, 9 slots are there, na? Okay. So now a question is two things we need to understand here. One is modified version of this. Little modification is there here, and another is that how many level of this tree we should have. How many levels of tree we should have? So here we had level tree. Here we just had level 1, level 2, and level 3 we had, right? So how many layers, how many levels we should have here in this tree? So for that, suppose I am having Q stations ready, right? And assuming that such Q stations are distributed evenly here. Suppose 4 stations are ready. So assuming that they will be distributed evenly here on this we want like it should be even distribution. It should not be like one side it is loaded and one side is full of ready station and another side is simply empty. We don't want that type of distribution. We want we want to create a tree where the distribution is uniform, so that whenever if all the stations are ready here, na, this slots will go empty and here collision will take place. So that type of situation we don't want. We want that uniform distribution should take place, right? So what exactly we want here? Suppose so under what we need here is, suppose this is level 0, this is level 1, this is level 2, right? So what I need, that if 4 stations are ready, all 4 stations will be ready under this node. How many stations are ready under this node? Here all 4 stations are under this node. 2 stations are under this node because this and this, and only one station is under this node, right? That means if you will observe, this is q into 2 raised to minus I. What is I? I is the level, right? So q is what? 4. What is I in my case? I is 0 here, 1 here and 2 here, number of level. So this will be 2 into 2 raised to minus 0, which is nothing but 1, and hence what it will be? 4 into 1, that is 4. What will be here? I is 1 here, so it is 2 raised to minus 1, that is 1 by 2, right? So 4 into 1 by 2, that is 2 here. And what will happen in the last level? What will happen here in this level? So it is 4 into 2 raised to minus 2. That is what? 2 raised to minus 2 is 1 by 4. 4 into 1 by 4 is 1. That means at this level, only one node is ready. That you can observe here, right? So this is what q into 2 raised to minus I indicates. It indicates that number of ready station under the particular node. Number of ready station under the particular node. Number of ready station under the particular node. And what we need, if it is whenever, if what I need here is that whenever I want that whenever there will be only one station ready under this node, under the node, then it will be a successful transmission. Suppose there are 4 stations ready under this node, so whenever I will get chance here, there will be collision because all 4 stations will transmit together, right? Your 2 stations were ready together, that's why collision will happen whenever the chance will be given here. What I need, that I should have I such a way that that whenever I do this situation, at that time the number becomes 1, right? What I need, that means number of station ready under the level I must be 1. That means I must have it. Otherwise, what will happen if I'm not having that type of level? That then what will happen? All the stations which are ready under this one are going to transmit, and that there will be collision that will take place. So if I will solve this one, then I'm going to get is 2 into 2 raised to minus I, that is 1 by 2I, 2 raised to I is equal to 1 by q, right? That means I'm going to get is 2 raised to I is equal to q. That means my I is that is log q to the base 2. What is q? That is number of stations ready, and my label, I should have my tree with I labels, where I is given by this equation log q to the base 2. How I obtain I? I obtain I such a way that I should have labeling in such a manner that I should at least have I should have one station ready under the node. If I will have very less number of labels only, if I will have just 2 labels, I will never get the situation where there will be only one station ready under the node. Every time I will have more stations ready, and every time there will be a collision. Understood? So I must live in such a level that at least one station individually becomes ready, and hence it will get chance to transmit. Okay. Now, the final variation of this is what I talked about. Now, one improvement is remaining, and that we need to understand first. That improvement is Bersica's and Galler distribution, or we can say their algorithm. What their algorithm says, what their modification says. Let us do it quickly. And you will understand it. Suppose only station G and H is ready. Assume that station G and H is ready. Only G and H, no other station. Only G and H is ready. Do the adaptive tree walk protocol quickly. Slot 0, who will transmit? Be fast. Slot 0, who will transmit? G and H are ready. Slot 0, who will get chance? GH, right. GH. Slot 1. So there will be collision. So depth first. Slot 1. Who will get the chance? No. See, what is algorithm? Algorithm doesn't know what how it will follow. That is what I'm asking you. Slot 0, right? Slot 0 is observed. Now collision happens. What algorithm says? Go depth first. Who will examine now? Which node will get examined now? Which node will get examined? 2. Of course. So go by algorithm, right? Go by algorithm. So 2 will get examined. Who will send here in who will send in 2? No one. So it will be empty slot. It will be empty slot. Of course, it can be empty slot. Why? Because no one under 2 is ready to transmit. Suppose it is empty slot, then what to do? Suppose it is successful transmission or it is empty slot, then you are going to ask your neighbor, right? So next slot, in next slot, who will get examined? Because it is empty. Logically, you can understand no one under this is ready. So see, no. See, algorithm, there is a thing like suppose here, suppose anyone can successfully transmit, then you were checking the neighbor, na? In the same way, what will happen if any unsuccessful any empty slot is there, then also you are going to check the neighbor. Because what is the meaning of empty slot? No one under this node is ready to transmit. So why to waste time here? So algorithm itself says that suppose my slot becomes my slot is empty, na? So then check your neighbor because no one under this node is ready to transmit. So why to check them? Okay. So no need to be sorry. Here it is actually it is a good idea that you were following the algorithm. That is really good. But that is how is happening, right? So what is the case? Two. So who will get in slot 2? Who will get examined? Which node will get examined? 3. And who will transmit? GH will transmit. True. GH will transmit. So collision happens. Then what to do? If collision happens, then what to do? Right. So sixth in sixth node will get examined. What will happen in sixth? If no one will transmit, it will be empty slot. Yes, it will be empty slot because of node 6. This is because of node 6. This is because of node 2. This is because of node 3. Right? Okay. In fourth slot, what will happen? Who will transmit? Seventh node will get examined, and who will transmit? DH. Both of them will transmit. GH will transmit. Right? Okay. In fifth slot, what will happen? G will transmit, and in sixth slot, H will transmit. So totally, we took 7 slots to resolve the contention, right? But now, what is this modified algorithm says? What this modified version of this algorithm says? Suppose you checked here, collision happened. You checked here, right? It was empty slot. That means should you check here? Why to check here? Because here collision happened. That means multiple stations were ready. You checked here, there were no station. That means definitely multiple stations will be there here. So instead of checking this, can't you directly go here to save a slot? Right? And that is what the modified algorithm is. So if there was a collision in the parent node, right? And there was empty slot in the first child, then do not ask the second child. Directly go to the next level here. Because definitely collision is going to take place here. Right? So now, so what we will not do? We will not ask this node 3. We will directly ask node 6. So what will happen in node 6? What will happen in node 6? No one will transmit. So should we check 7? Should we check 7? No. Next level, that will directly we should ask D. So we should not ask seventh node. We should not ask seventh node. We should directly ask G will send and H will send. So how many slots now we will take to resolve the contention? How many slots we will take now to resolve the 5 slots? So we save 2 slots. Okay. So this is what the modified version of the algorithm, right? So if empty slot becomes, do not ask the sibling. Go to the next level itself, right? So this is all about adaptive tree work protocol. Okay, in the laboratory, we will go with the network commands and laboratory parts. So we are not going to discuss theory today. We will go with the laboratory discussions only. Okay, any doubt? Okay, so you may leave for now.